correlation with other types of characterization methods so that a comprehensive understanding of nanoscale features and nanomaterials can be studied using this particular technique. Okay, so please feel free to interrupt whenever you want if you do not follow something so that I'll be happy to explain the same again and therefore it doesn't become too monotonous. All right, so let's get started with this. So um, yeah, so as you see from this slide, I briefly introduced my group. So we do two kind of activities as Dr. Srinivas introduced. We do one on the one hand what is called combinatorial alloy design, where we produce new materials both at micrometer scale and the micrometer scale. And on the other hand, we do what is called correlative microscopy. So one example of what we do in terms of this bulk composition that we design, and we have installed a unique material processing facility where we have a specified furnace which can melt most metallic materials in combination of other metals, and we can get them in the form of the hot liquid metal and pour it into a mold so that we will now be able to produce gradients of composition from a single master alloy into a mold which can be a single mold as well as a partition mold, so that we will now be able to get whole range of compositions covered by this single process. So which is typically called the combinatorial alloy design, where you can design materials of different chemistry from a single step of processing so that all exterior parameters remain the same. The other half of our profile is the correlative microscopy, where we try to utilize the material synthesized in this method as well as tested for either magnetic property or a mechanical property into a comprehensive characterization where all the analysis at the nanoscale happens on the same sample volume. So this means we tend to produce a sharp needle which is required for atom probe tomography, and we do crystallographic analysis inside a microscope where you can now see the different orientations of a relatively sharp. If you see the scale works around 100 nanometer, so we have a tip that is produced with 50 to 60 nanometer in diameter, and in that tip we have an interface. So therefore you can see the two different orientation of the crystals in two different directions, and that particular interface, if it may have a different chemistry, it's usually very difficult to get it characterized by conventional methods. So we tend to use this correlative approach where we introduce this tip into the atom probe tomography so that we are now in a position to get the chemical composition information of this tip of that particular interface identified in atomic resolution using this method. So that means we try to combine the crystallographic information and the chemical information at nanometer scale on the exactly same analysis volume so that there is no discrepancy in the end in terms of understanding the materials properties. So this is a broad theme of what exactly my group at IIT Madras is doing, where we produce alloys of different chemistry as well as we analyze them, we test them mechanically, magnetically in other ways, and finally we end up characterizing them even until almost the atomic resolution as what you see here. So this way of analyzing materials until atomic resolution is possible because of this National Facility for Atom Probe Tomography, which is coming under the umbrella of NFAPT. So this NFAPT is a consortium established originally by this 8 different partner institutes, which include 6 IITs and 2 national labs. And all the 8 institutes utilize this facility every day. So we are running in a 24/7 mode, 365 days. And as you see in the Indian map, all the institutes are distributed across the country, and we have for every state and every region there is a coordinating lab, which can be, for example, for Bombay it can be IIT Bombay, or for the southern region it can be either ARCI in Hyderabad or IIT Madras in Chennai, where we accept proposals from even other institutes, and every institute listed here has one 8-hour slot every week, and therefore we are able to measure their samples in atom probe tomography, where we prepare the samples at IIT Madras and the partners can remotely operate this microscope sitting in their own lab without the requirement of coming to IIT Madras. So in this way, we have been enabling this advanced microscopy for a wide range of materials so far. And until now, we have done more than 4,500 measurements in the last 4 years of this facility being in place. So if you want to know more details about this facility, you can go into the website, which is nfapt.iitm.ac.in. There you will get all the information. So Now this is how this NFAPT operates. Now I explain you what is under the umbrella of NFAPT and how we are utilizing for the modern day research where we deal with nanoscale features. So as I said before, we have 8 different partners which are partnered together to establish this facility. And under this facility, we have these 3 unique microscopes. So the leftmost one is the dual beam focus ion beam, which we utilize to produce the samples necessary for the atom probe tomography, which is the middle picture here. So this is the most advanced microscope that we have. And to support the functioning of this facility, we also have what is called a transmission electron microscope. That means in the dual beam microscope, we will be now able to produce samples necessary for transmission imaging, or we can do to a large extent transmission imaging inside this dual beam microscope itself. And we produce the sharp needles, which is necessary for this atom probe tomography. And this is a local electrode atom probe that we have here. And in the first part of my talk, in the first 40 minutes, I'm going to talk only about the fundamentals of this particular technique and how this technique is relevant and useful for modern day nanoscale materials characterization. Okay, so and as you know, if you do a normal scanning electron microscope based imaging of materials together with orientation mapping, you will now be able to see this microstructure with orientation details and possibly the phase analysis that you can do. But sorry, if you want to have a localized information, that means in certain region, for example, this interface, if I want to know the exact chemical composition of the interface, or if I want to know what is the crystallographic details at the interface, then for the crystallographic details, we can go into the transmission electron microscope by preparing a sample out of this region of interest. Whereas if you want to know even a ppm level dopant sitting in certain interfaces, then TM may find it difficult to explore. So therefore, we require this kind of local electrode atom probe where we can see the 3-dimensional distribution of the elements present in inside any of the 3D volume. And accordingly, we can rotate, we can look into the heterogeneity. For example, you see this nanoscale copper clustering or a precipitate that is visible in this image. And all of these things, therefore, we can study using this atom probe tomography. So therefore, my talk is going to be split in this way. The first 40 minutes, I'll present about the basics of atom probe tomography and the principle by which this is working, and the sample preparation requirements if you want to measure anything using atom probe tomography. In the second part of my talk, utilizing this understanding, I'll explain with at least 2 different case studies how this technique has been relevant for those materials that are in application, for example, the soft magnetic material, and as well as the self-healing materials is the newer generation type of materials that are emerging, and how this technique has enabled us in understanding these two. And finally, I conclude my talk in the end with introducing what is called correlative microscopy. And this is absolutely crucial for the study of additive manufactured materials, which is again a very rapidly emerging field of materials research. So to start with, we'll go with the general introduction of what is this term tomography stands for and why we require to understand the term tomography if we now want to study about this atom probe tomography, which is the atomic scale technique. So this tomography is basically indicating that anything that we can image in a 3-dimensional way, either by serial sectioning in 2D form, or we can use it in a bulk way, as you saw in the atom probe tomography, is something that represents in a 3-dimensional space is called tomography. That means you can now have a cube or a cuboid, as you see here in 3 dimensions. And inside a cuboid, if you have 4 different objects, for example, a cylinder, a sphere, a truncated cone, or a half-cut sphere, if you try to image any of these objects in a projection microscopy, that means if you take a transmission electron microscope using the electrons, if you see from one direction to the other, you get a projected image like this. This 2-dimensional projected image of a 3-dimensional object includes all these structures which are present inside, which are those internal structures. But as it projects onto the screen, what you end up seeing is that the cylinder is seen in the form of a rectangle, the sphere is seen in the form of a circle, the half-cut sphere is seen in the form of half-cut circle, whereas the conical form is now looked at like a triangle. But this is not the true representation of what the original 3-dimensional object looks like. And therefore, we require advanced techniques because this is sort of a preliminary information, but not a complete information. It's like misleading information because the three-dimensional features are not visible anymore, and the dimensions are now interpreted in a very different way. So if you want to get better with this kind of a real description of the objects in three-dimensional space, then you can slice layer by layer of this object. That means you can produce a slice S1, which is somewhere in this region, and look through the projected view using the microscope. Then you can see for the slice of S1, probably from this region, it includes only a triangle and a rectangle. But if you have multiple slides from this region, then you see the dimension of the rectangle decreases and the dimension of the conical volume, which is a triangle that you see in the projected view, also changes. Now, if you stack all of these multiple slices together, that means slice 1 relates these two objects, slice 2 relates the objects which is spherical and half-cut sphere. By adding all the slices one after the other, you can also three-dimensionally reconstruct whatever that is there in this original volume and say this is a true representation of a three-dimensional imaging. That means anything that you have in a nanoscale, and that nanoscale has a specific morphology. If you do only a single projection imaging, you may not get the full description of that particular morphology. But if you, on the other hand, do the slicing and look through the different slices of the same nanoscale feature, then we have a much better chance of identifying the real description of this morphology of the features. And therefore, we will now be in a position to put these things together and then see them in the real or the more realistic descriptive way. So this is something that has been going on for a long time, which is therefore coined as tomography, where we want to image something as a three-dimensional object, which remains in three-dimensional after imaging. So if you now put all of these tomographic methods into a context, that means as a function of the resolution with respect to the field of view covered, if you now want to see what are the different three-dimensional techniques that are available where any object can be imaged in 3 dimensions. Then the coarsest form of three-dimensional imaging, which is tomographic imaging, is based on X-rays. So you can use an X-ray microscopy. And then if you try to image using X-ray a three-dimensional object, then the resolution that you can resolve is somewhere in the range of a micrometer feature with a field of view as large as a millimeter. That means you can have a large millimeter volume covered, but you can resolve features only about 10 micrometer, not less than 10 micrometer. But if you want to go into the nanoscale range, then you can use the other methods like focus ion beam, roughly in the range of 100 nanometer, and a field of view of 100 micrometer. So you can have multiple particles of nanoscale features imaged with certain statistics using focus ion beam serial sectioning, as what I showed earlier. Or you can go into further details of X-ray mapping of EDS coming from a transmission electron microscope or an electron energy loss spectroscopy in a transmission electron microscope. That means going higher in transmission mode with serial sectioning, you can improve the resolution, but at the cost of the field of view. You may not get significant statistics because the field of view is decreasing as we now go finer and finer in resolving the details. So in that context, the Arab probe tomography is in a unique space where, as you see here, the resolution is less than a nanometer. That means we are talking of a possibility to see individual atoms in the angstrom range and collect these individual atoms over a range of possibly, with the modern generation, even 1 micrometer field of view is something that can be covered. That means this is the only technique where individual atoms can be resolved individually over a large field of view, considering the resolution that we get in the atomic scale. So now the question is, why do we need to do this kind of a high resolution three-dimensional imaging, which is a tomographic imaging at atomic resolution? Because to understand most materials, so any material that you have in a common day life or anything that you do in a research lab, they're all complex. There can be multi-component, there can be multi-phase, nanostructure, there can be equilibrium, non-equilibrium, solubility changes as you have these variations. Then they can have complex nanostructural features. That means the morphology can be complicated. They can have local partitioning, segregation, etc. And there is always a correlation between what is a nanoscale structure and how does it impact the property of the material. If you want to now understand any of these features in any material that is of interest, then we definitely need to look into the possibility of seeing them in a nanoprobe tomography so that you get the three-dimensional morphology with precise chemical identity and quantification of local chemistry so that you can now be in a position to tackle a lot of materials problems that can be the phenomena occurring at atomic or a nanometer scale, or we can get information about the elemental distribution in the real space. That means inside the material, how they are distributed. Are they partitioning locally, probably at the interface, or are they going to any other region, or there is a phase stability difference leading to a formation of a new phase as a function of thermal treatment, decomposition, etc. Or you can also talk about nanoscale diffusion processes when the material is subjected to some kind of thermomechanical processing. So for all of these effects that happens in most materials, we need to get the three-dimensional imaging at near atomic resolution. And to that extent, the materials that are suitable to be studied by this technique of atom probe tomography includes metals, alloys, and that can be semiconducting, as well as these days we can do ceramic material imaging as well. So to an extent, porous materials and biological materials can be studied. It depends on the stability of the material, and the organics are a little bit difficult to do, but liquid materials we cannot do with this particular technique. So now to understand the requirement, now we move on to understand how this technique evolved. I mean, how the story of atom probe microscopy began. So a simple description to share the history of this particular microscopy. It was first coined by the person called Erwin Muller, as you see in the picture. He's called the father of high field nanoscience. That means his curiosity to image individual atoms from nanoscale features is the source of the development of this particular technique, and therefore he is called the inventor of the atom probe tomography or a field ion microscopy. So that means when it first started, he produced a sharp tungsten wire, and to that tungsten wire he applied negative polarity, and on a phosphor screen he applied positive polarity. So what he saw in the beginning was a distribution of the charge cloud, as you see in this image. Depending on the orientation of the grain, we were able to see the charge cloud distribution, but not a real atomic scale imaging. So therefore, he tried to reverse the polarity. That means on the same tungsten needle, he applied positive potential this time and the negative potential to the fluorescent screen. Now what you saw dramatically different was an individual white spots in the fluorescence screen, which is now representing individual atomic positions. That means he started evaporating atom from the surface of this needle, and those atoms were impinging on a fluorescent screen, and all of these atoms now look like, as a result of the fluorescence, a white dot. Now, if you connect all of these dots, you see a kind of a circular arrangement, and there are also crystallographic poles that are visible as smaller circles. Now, this is the starting point of what is called high field nanoscience, that extreme positive potentials are applied to the tip, and because of a negative potential on the screen, the atoms are evaporated in the form of the ions, and all the ions, because of the negative potential on the screen, impinge on the phosphor screen and end up producing this fluorescence image. So this fluorescence image and the position of the image therefore enables us in identifying the orientation by which this tip was present, and accordingly the atomic positions being precisely identified. Now, based on this technique of field ion microscopy, he later went on to develop what is called today's generation atom probe tomography. So now we will go into the atom probe tomography and try to understand the principle of how this atom probe tomography works. So like I said, we need to produce samples in the form of a very sharp needle of 50 to 60 nanometer in diameter, having a hemispherical cross section. Now to this tip, we apply positive potential. If the material is fully conductive like a metal or an alloy, then in addition to the positive potential, we can also apply a short duration pulsing of electrical pulses with certain percentage. So that means at each point in pulsing, the atoms present at the apex region of the tip or the periphery of the tip, they get ionized because the potential applied is sufficient enough to induce a bond breakage and the atom becomes an ion. That means one or two electrons are given away, atom becomes an ion. And because there is a negative potential in the detector end, these atoms are now directed towards the detector by the field lines that are existing between the sharp needle and the detector. And this trajectory followed by the atoms enables us in identifying what is called a chemical identity, because every different atom by the color code, as you see here, will have its own atomic mass. That means for a fixed distance, each atom is going to take its own time to reach this detector space. That means if you know the distance already between the sample and the detector and the time taken by each of the atoms to reach the detector, you basically can calibrate what is the element that is being reaching the detector in any given time. So now when you couple this mass identification, something like a mass spectroscopy, using the time of flight as a fingerprint to identify the chemical nature and combine it with the pulsing behavior. That means you trigger these pulses to enable this evaporation, and every pulse that is given is now taken as a T0 of the time window, and the time taken by the atom to reach the detector is taken as time period 1. So between 0 and 1, you now collect all these atoms reaching the detector, and using that as a fingerprint, you can now get what is called a mass spectrum. And this spectrum now indicates the different types of the atoms present in the material reaching the detector in different time scales, identified in terms of mass to charge state, and the number of such atoms reaching is now represented in terms of the counts on the y-axis. So for each chemical species, you will now be able to see isotopically resolved mass spectrum where individual peaks represent the different isotopes of each of these materials present inside this analysis volume. Now, taking this information into account of the mass spectrum for chemical identity, together with the detector position, that means the X and Y position on the detector over which these atoms were hitting as ions, we will now be able to three-dimensionally reconstruct whatever atoms that are evaporated from the apex region of the tip, so that we are now able to see this entire three-dimensional volume being reconstructed. And the scale on the X and Y, as you see on the Z, these are all in nanometers. That means we are now able to see individual atoms visualized and their atomic arrangement also being visualized in 3 dimensions. We will now also be able to quantify the chemical species present across these nano-laminated layers one by one, and also we can collectively see their distribution. This means, in simple, the atom probe tomography is a combination of a time of flight mass spectroscopy that is useful for chemical identification and an ion projection microscopy, because the detector X and Y position being utilized to reconstruct this into a three-dimensional volume. And therefore, we can say this is also an ion projection microscopy over a fixed distance of X between a sample and the detector. So I hope this has given you an idea of what we are trying to do on a real-time material and how we are able to see the atomic scale features in a three-dimensional volume. So if you now want to see this real time, so this schematic now tells you that we apply positive potential. Now we apply laser pulsing or a voltage pulsing. The moment you trigger the pulse, an atom at the apex of the tip becomes ionized, travels through this fixed trajectory, reaches the detector. As it hits the detector, we will now be able to see the X and Y position over which it hits the detector, and the time, which is the time taken by each individual atom to travel the same distance, which is the time of flight. Now, using this three information, over a period of time, we keep collecting atoms by continuously pulsing it. And over a period of time, you collect all of this information. And using this XY position and the time of flight, we will now be able to three-dimensionally reconstruct whatever volume that is lost on the apex region of the tip. So that means the technique is destructive, but at the same time, you will now be able to collect all the atoms on the detector, and therefore you can utilize the position of the detector and the time of flight to reconstruct into a meaningful three-dimensional volume. That means any nanoscale feature you will now be able to resolve atomistically in 3 dimensions. So an advancement to this technique, what we have at ID Madras is the use of this local electrode. I mean, this particular object that you see also has a negative bias. That means it enables in condensing the field around the needle, and therefore we will now be able to get a better resolution from a localized volume of this tip. And there is also a reflectron where you increase the time of flight twice by making the atoms move around the same distance 2 times. Therefore, you get a better mass resolution, which we'll cover as we go along, what is called mass resolution. Anyway, now the use of the local electrode can be distinguished when you look into this slide. So this is the presence of a local electrode, as you saw in the earlier slide, and the top half is the absence of the local electrode. So the positive potential that you apply to the tip and the negative potential to the detector. In the case of the local electrode, you can see that the field is more condensed towards the apex region of the tip compared to the case when there is no local electrode. That means if you are able to condense the field around the apex region of the tip, then you will now be able to get a reasonably better resolution, as you can see in the detector event map, which enables us, therefore, in resolving the nearest neighbor atoms in a much better way. Okay, so now this local electrode atom probe, as what you have seen, and this is the overall view of this microscope. So anybody across the country will now be able to access this facility as I indicated before. So you just have to send us a proposal either directly to us or to the nearest institute that you have. I think for those people in the Vijayanagaram region, you can contact the RCI in Hyderabad, where they are the nodal agency for most of this region. And if you send the proposal for your research activity, if the proposal is accepted, you can send the sample. We will prepare the sample, insert into this microscope, and you will be given remote access to operate the microscope sitting at your home or in any of your institutes. So therefore, this is quite a unique facility which you can make use of. Okay, so now to go a little bit into the physics of atom tomography. You have seen the principle, how the atom by atom we are removing from the material and how we are able to detect atom by atom as the atoms become ion and reach the detector. So now to understand the physics of it in a simple way, now take that there is a layer of atoms and there is one atom sitting on the apex region. If you now want to move this atom from this position to this position, that means over a distance of x, if you want to move this atom, it's impossible to move this without breaking the bond. That means you have to break the bond. The moment when you break the bond, that means 1 or 2 electrons are being given away. So when you give away 1 electron, then the atom becomes an ion and takes a charge of n plus. That means a single charge state represents 1 electron from an atom has been given back to the material. If you now want to understand that how can we get this atom ionized by moving this atom over a distance of x, then we have to look into the simple potential energy versus distance diagram as we studied in the high school and the first year bachelor's, where at a critical distance, there is a minimum energy. That means the energy between repulsion and attraction is balanced. And therefore, there's a critical distance of x over which the atom stays with the nearest neighbor distance. But now you want to move this away from the nearest neighbor distance, then in an ideal condition, that means in an equilibrium condition where there is no external field applied, that means you can now see the Q naught therefore represents the activation energy required for an atom to move from an ideal position to a distance away from this atom position. That means Q naught is a significant amount of energy we need to have. We need to be applied to the atom so that it can move away from distance. Whereas now, as we saw in the principle of atom probe, we apply positive potential. That means we create a field around the sharp needle by applying the positive potential. And as and when the potential is applied, the barrier required to be overcome for an atom to become an ion decreases. So now the QF stands for the activation energy of a condition where an external field is being applied to the material so that the barrier required to overcome in the absence of the field, which is Q naught, is condensed or reduced to the value of QF, which is very minimum. That means when you apply a external field, as in this case of atom probe tomography, the potential energy versus distance curve becomes so low in terms of energy over a distance of x, and the minimum energy of QF therefore can be obtained, and the QF is therefore can be calculated based on the binding energy of the surface atom with respect to the material where over which it is sitting, and the ionization energy, which is therefore standing for whether it is a one plus charge state or 2 plus charge state. That means whether it is ionizing by giving away 1 electron or it is ionizing by giving away 2 electrons, etc. It depends on the external field F which is being applied. That means when the field is going to be intense, the more number of electrons, which is Ne stands here, is going to be given away to the base material before the atom becomes an ion and moves away in a distance of x. So therefore, using this expression of QF, one can now say the activation barrier is reduced as and when an external field is applied compared to the activation barrier of Q naught, which existed when there was no external field. Now, having reduced the activation barrier for the atom to be moving away from the surface into a free volume, we can now make the process continuously happening by a certain constant evaporation rate. That means we can now define an evaporation rate by applying the external field and increasing the magnitude of the field so that there is a continuous evaporation given by this Arrhenius expression, which takes into account the temperature as well as the Boltzmann constant. So now how this continuous evaporation translates into a meaningful mass to charge state. If you want to now understand this particular relation between an atom getting an ion and then evaporating from a surface moving across a distance x, how can that be translated into a chemical identity? That means we are now applying an external potential or a voltage which is given as U, which is applied voltage for a given sample of a hemispherical cross section with a defined radius. Now, because of the applied voltage, the electron gets excited or gets polarized. And because we are applying positive potential, that polarized state means there is an electrostatic potential energy provided, which converts the atom in the form of the ion and provides the ion the necessary kinetic energy given by half mv square. Now, this kinetic energy drives the ion to move away over a distance of L, which is the flight distance L, with a fixed time of t. Now, that time of t over the distance of L is determined by what is called the atomic mass. So that means the ion velocity basically depends on the distance traveled by a given atom over a period of time. And that velocity, if you now replace in the kinetic energy expression, we'll now be able to get what is called the mass to charge state, which is governed by the time of flight t taken by each individual atom to reach a fixed distance of L between the sample and the detector. So in this way, you can now get for every evaporation of an atom in the form of the ion moving a distance of L over a time period of t, you can now define what is called the mass to charge state, depending on whether one electron is given or two electrons have been given. So this way, you can now have the relation between a continuous evaporation of atom for a given sequence of pulsing and making the atom translate into an ion by giving away one or two electrons, moving over a fixed distance of L for a given time period of t determined by the atomic mass, which is the M. So by that, we can now get this mass spectrum for any multi-component system. And now isotopically resolve element by element. That means every element in the periodic table has their own isotopic abundances. As you now see in this particular image, iron, for example, has 4 different isotopes with different natural abundancy. And similarly, chromium has 4, carbon has 2, and hydrogen has 3. So like that, every element in the periodic table has their own isotopic abundances. Now, whenever you see a peak, the relative intensity variation of the peak represents their typical isotopic abundancy variation. Okay, so now identifying the peak with respect to mass to charge state, assigning that particular peak position for that particular element removes all ambiguity associated with chemical analysis. That means the nearest neighbor elements in the periodic table, for example, iron, for example, chromium, for example, manganese, for example, nickel, all these 4 are next to each other in the periodic table. If you go with any other spectroscopy method, it becomes extremely challenging to distinguish all these. Whereas in the case of atom group tomography, each of these peaks now can be isotopically identified and without any ambiguity can be assigned for their particular elements. So therefore, in a way, this mass spectrum defines all the elements present inside in the periodic table being detected and identified with their isotopic abundancy. Therefore, this brings the question of what is the mass resolution that we can get. Now, each peak that you saw in the mass spectrum has a defined width. Now, that full width, you can now measure either a half maximum or full width, you can measure a tenth maximum. And for any given microscope of atom probe, you can now say this particular mass spectrum had a mass resolution given by this delta m by m, which delta m stands for the full width at half maximum or full width at tenth maximum. Okay, so that way you can now define the quality of a microscope with respect to the mass spectrum that we are getting. So like any other microscopy method, this method also suffers from certain kind of a artifact. That means any variation to the local configuration or the arrangement of atom is being now seen as an artifact. So this artifact, one of the artifact is called the local magnification effect, as you see here. So now when you have a heterogeneous system where a precipitate sits in the matrix, now the precipitate elements have very different ionization potential, or the matrix has very different ionization potential. If it's a single phase material or single element, then there is no problem. There is a uniform evaporation all the time when there is a pulsing. But when you have a two-phase material and there is a difference in the evaporation field, then you can have image overlap depending on whether the elements of the precipitate beta has a higher evaporation potential compared to that of the matrix. If we have the opposite situation where the elements of a precipitate has a lower evaporating field compared to the matrix, then there is going to be artificial vacancy visualized between the precipitate region and the matrix region. And this is something called the Achilles heels of atom probe tomography. An example of this is something that you can see here. When the evaporation field of certain species is going to be lesser compared to that of the matrix, then you see a condensed situation of the precipitate being visualized. And as and when the ratio between the evaporation field of A and the evaporation field of B, that means the two different materials that are constituting matrix and the precipitate, when their evaporation field becomes more or less similar, then you can see the distribution is also going to be similar without any artificial condensation that's possible. Now, when the scenario gets reversed, where the evaporation field of the element B is going to be now higher than that of the evaporation field of the element A, then you can see there is an artificial magnification that is coming in with the vacancy that you can see in between. That means that there is a distortion in the localized region, which therefore prevents from looking into the actual morphology of the precipitate present inside. This is one of those typical or a critical artifact that you get in the atom probe tomography. Similarly, there is a possibility that a hydrate formation for most elements can happen in an atom probe. Even though the atom probe works in an ultra high vacuum condition, there is a possibility that certain elements can attract hydrogen inside, and that hydrogen therefore can be imaged together with these elements present. For example, in the case of aluminum, magnesium, silicon alloy, you can now see next to the main peak of this particular case, you can now see the hydride peaks that are being visualized. So this hydride therefore is forming invariably because hydrogen can diffuse into any ultra high vacuum conditions and react with any element present inside the material, and therefore we will now be able to see hydrides also as part of this analysis. Okay, now I move on to the last part of this first presentation, which is the sample preparation required to do atom probe tomography. I hope you understood what is atom probe, what is tomography, and how the atom probe works in principle, so that you can now see nanoscale features at near atomic resolution. Now, the sample preparation, therefore, is going to be critical because the starting material itself is a 50 nanometer diameter hemispherical tip. So therefore, the sample preparation has certain skill levels required to prepare and certain constraints needs to be met. And this is the first part of the sample preparation. That is, the most conventional way of preparing atom probe samples is by electropolishing. That means we can now draw a wire or a rough plank, and you cut this rough plank and subject this rough plank to electropolishing. So when we now do this electropolishing, that means you can now need a microscope because your eyes cannot see beyond certain limit. And now as you look through the microscope, the sharp needle gets into a loop with an electrolyte. You take it in and out by applying the potential between them. So every time the loop goes in, there is a material that is being dissolved, and you can now relate the dissolution rate of the material with respect to the applied current versus applied voltage. So there is a typical plateau range, which is called polishing. Now we should be within the range of B and C, which is polishing, where the boundary, which is etching, that is only creating a surface reaction, but the polishing means you are removing the material out of the region that is exposed to the electrolyte in the presence of the applied voltage as well as the current. And if you extreme or if you increase the voltage and the current, then you start ending up doing pitting corrosion. So therefore, we now have to be within the range and monitor the evolution or the materials removal under a microscope. Then you will now be able to see that from a raw blank, which is this image number 1 here, we can now start slowly decreasing the size or making the tip sharper and sharper. And at the highest magnification, you can now see the resolution of the microscope. The optical microscope becomes limited to resolve these features, which is almost now 50 to 60 nanometer in diameter. So you go into a scanning electron microscope, inserting the needle, and then verify the dimensions in terms of the size that you want. So typically 50 nanometer is the dimension required to be inserted into atom probe tomography with a given Shank angle of somewhere in the range of 20 degrees. Now this is an ideal tip that can go into atom probe tomography, and you can now evaporate atom by atom from the apex region of the tip. The more sophisticated way to produce the same needle is by using the dual beam focus ion beam, which I showed in the beginning. So this is something comes under the umbrella of NFAPT, where we have this dual beam microscope, where we can now produce the same kind of a needle in a much more sophisticated way. That means if there is any specific region of interest to be studied, we can now prepare using this method, which is not possible by conventional electropolishing method. And also, if you want to do thin films, if you want to do semiconductors, if you want to do insulators, ceramics, etc., then electroporation is no longer possible. And this is the only method by which you will not be able to produce samples for atom probe tomography. So there is a series of steps that we need to cover with certain skill level so that we will now be able to produce samples. I'll show you briefly how this works. So you can now insert any sample inside this microscope, what you saw in the earlier slide. Identify the region of interest and start milling on either side of the region of interest so that you can produce a cantilever by milling away material by gallium ions bombarding the surface. So you produce a sort of a cantilever. Then in the microscope that we can have a manipulation needle inserted so that that cantilever is now welded using a platinum deposition system. So it gets connected with this external manipulation needle, and then you can cut away the other side as well, and then lift out this free hanging cantilever out of the bulk material and take it to a substrate and deposit on top of the substrate by smaller slices of this entire cantilever into multiple segments, weld it together so that you can now have along each of these dots one sample ready for atom probe. So that means in the final step, from a wedge-shaped geometry, you now do this annular milling, which is again by gallium ion beam. You keep milling them so that you get the sharp needle ready for atom probe tomography. If you now want to do the same set of process for example, on a grain boundary, that means you now want to specifically look into one particular interface of a material. Then you can also do that, identify the interface, apply a platinum coating to protect the interface from external beam damage, and produce the same process by the series of steps that you saw so far. And you can even verify the presence of a grain boundary by a cross-section imaging in a microscope where the different grains or two different grains diffract the electrons differently or scatter electrons differently. So you see a two different contrasts and you mill it on the middle. Then you can say this interface is now captured within this little volume of 1620 nanometers, which is now good enough to be measured in atom probe tomography. Now these kind of needles goes into the atom probe, and the measurement works under certain specific conditions. That means the measurement doesn't run at room temperature. So there is a range. That means you want to image individual atoms, meaning you do not want atoms to vibrate randomly. That means you want to freeze the atoms on the surface of the needle so that the X and Y position of the atom position can be mapped on the detector as long as it is remaining freezed. That means you can now look into these parameters, for example, the temperature. When the material is freezed, for example, to 20 Kelvin or 40 Kelvin, you can see all the individual dots, which is representing one atomic position. All these dots are individual atomic position. These are all nicely being visualized. It again depends on the material and their conductivity. You can now play with the temperature. And for a given copper with titanium alloy, you can see the resolution gets poor if you go to 80 Kelvin. And the resolution is very good if you are in the range of 40 Kelvin or 20 Kelvin. So depending on the material, you can now play with temperature as a parameter, limiting the vibration of the atom on the surface of the material so that we can now get the best possible resolution obtained from the atom probe tomography. Likewise, we have a range of parameters to be considered, and all of these parameters are summarized in this particular slide. So depending on the rate of data collection, that means the number of atoms you want to collect in a given time, you can now control the different parameters, which is the temperature and the success yield and the resolution that you can get. All of these things are typically impacted by the parameters that we select. Okay, so I think with that overview, I summarized this part where we have certain definite advantages by this particular technique for nanoscale materials characterization, and there are some limited drawbacks. So first, the advantages is we can now see the real three-dimensional distribution of atomic arrangement in real space, not in a reciprocal space. So that means real space imaging is possible together with a very high spatial resolution. That means a 2 angstrom nearest neighbor atom can be resolved in the X and Y direction, and a 1 angstrom resolution can be obtained in the Z direction. That means each individual atom can be resolved in a three-dimensional space with a very high detection sensitivity, which is equal for all elements present in the periodic table. That means any nanomaterial, if you study, be it from a hydride till an oxide till a nitride, this technique has equal detection sensitivity for all these elements in the periodic table with a limit on detection sensitivity to ppm level of 10 ppm. That means you get 1 million atoms. You can easily see there are 10 atoms of such species present inside, and which this technique enables you to quantify them, image them in 3 dimensions, as well as quantitatively indicate for certain localized region how many of such species are present in atom percent or weight percent or the numbers that you can get out of this particular technique. The limited drawback that we have is because by getting this atomic resolution, we cannot have too large volumes to be analyzed. So there is a small probe volume involved. That means limited volume can be analyzed. And the method itself is destructive because you want atom to convert into ion, and that ion has to be detected. So there is a destructive method. And by the physical nature of the detector, only 50% are these days you can have a detection efficiency of 80%. That means everything that is getting evaporated, 80% of them can be detected easily. And there are some minor aberrations as what I showed earlier, where depending on the chemical configuration, you can have a minor changes in their morphology. Okay, so to conclude this part of the story, I summarize everything as what I showed earlier. If you want to know more details about this technique, you can go into these textbooks which are available these days. The latest one is from Baptist called this atom probe microscopy. So if you want any textbook, you can write to us. We can also share the e-version with you, which we are subscribed at IT Madras. So these textbooks enables you to get more deeper insights into this particular technique. If you want to now read in a very quick way, you can refer these review publications that have come over a period of time. The latest publication is from the Tom Kelly MRS Bulletin, where you can also have a comprehensive overview of this particular technique. Of course, the more advanced modern day review papers cover a lot more details, but the basics of the atom probe tomography you can study from this literature that I have listed down here. Okay, so I'll stop here for the first part. If you have any question, we can take it, or I think we can go for a break, as Dr. Srinivas Prasad has said earlier.
Sure, sir. For a short break, yes. For 10 minutes, we shall stop here, and with your convenience, we can start again, sir. Again.
Okay, so we reconvene. I mean, I'll keep it online. So I'll come. I'll switch on my mic again at 8 o'clock. Okay, and then we'll go in with the case studies. Is that fine? I mean, if there is any question, please feel free to ask. I'll be online.
Anyway, there is an interaction session, sir, at the end of this part 2.
Okay, then we'll do it then. Yeah. Okay, let's go for a 10-minute break.
Sure,
thank you.
Thank you.